Welcome to this explainer. We're diving straight into the fundamental building blocks of our universe today to demystify the wonderfully complex quantum mechanical model of the atom. If you've ever, looked at a solid object and wondered how it's actually mostly empty space, or how the universe organizes itself at the most microscopic level imaginable, well, you are absolutely in the right place. Let's get into it.
Here's our roadmap for today. We'll be hitting the flawed classical atom, the wave-particle quantum leap, Schrödinger's probable universe, the quantum address system, shaping the atomic world, and finally, the rules of atomic construction.
All right, kicking things off with Section 1, the flawed classical atom, a chronological mystery.
Science is really just a constantly updating draft. We started out with J.J. Thomson's model, where he imagined the atom as a positively charged sphere with electrons stuck inside it, kind of like seeds in a watermelon. Then, Rutherford comes along, does his famous gold foil experiment, and completely proves Thomson wrong. He showed that the atom actually has this tiny, dense, positively charged nucleus with electrons just sipping around it. After that, Niels Bohr took it a step further, suggesting electrons travel in fixed, circular energy orbits, much like planets around the Sun. But as elegant as Bohr's little solar system model was, it had a fatal flaw when you applied it to anything more complex than a single hydrogen atom.
So here's the mind-bending catch. Classical mechanics predicted that an atom shouldn't even exist. According to standard electromagnetic theory, any moving charged particle, like an electron orbiting a nucleus, should continuously emit radiation, lose its energy, and just instantly spiral inward, crashing right into the nucleus. Think about that. If classical physics was totally right, literally all matter in the universe would collapse in a fraction of a second. But obviously, atoms are incredibly stable. This created a massive, glaring mystery for physicists to figure out.
Moving right along to Section 2, the wave-particle quantum leap, breaking the rules.
It is fascinating to look at the macro versus the micro here. Louis de Broglie proposed that all forms of matter have a wave character. So you might be wondering, why don't we see everyday objects acting like waves? Well, let's just look at the math. If you take a heavy 6.626 kilogram iron ball moving at 10 meters per second, its calculated wavelength is 10 to the negative 35th meters. That is unfathomably small, completely imperceptible. But take a microscopic electron, which has a mass of about 10 to the negative 31st kilograms, and suddenly its wavelength becomes highly significant compared to the size of the atom itself. Wave-particle duality really only matters when things get incredibly tiny.
And because of this weird dual wave-particle nature, Werner Heisenberg realized there's a fundamental limitation hardwired right into our universe. You simply can't know exactly where an electron is and exactly how fast it's moving at the same exact time. If you measure its position with really high precision, its momentum becomes a total blur, and vice versa. The very act of trying to pin down a quantum wave particle alters its state.
Which brings us to Section 3, Schrödinger's probable universe, a new reality.
Now, instead of fighting this uncertainty, Erwin Schrödinger totally embraced it using some highly advanced math. His wave equation proved we had to completely abandon Bohr's idea of fixed planetary orbits. I mean, if we can't know the exact path of an electron due to Heisenberg's uncertainty principle, we have to think in terms of probability. So Schrödinger introduces the concept of the orbital. Notice that subtle difference in the word. An orbital isn't a set path. It's this three-dimensional cloud of space around the nucleus where the probability of finding the electron is at its absolute maximum. We essentially traded certainty for probability.
Next up, Section 4, the quantum address system, cosmic architecture.
To actually navigate this probability cloud, every single electron in an atom is assigned a set of 4 quantum numbers. It's basically a cosmic mailing address. The principal quantum number, n, represents the main energy level or shell. Think of this as the city the electron lives in. The azimuthal quantum number, L, represents the shape of the subshell. That's the street. The magnetic quantum number, m, represents the orbital's orientation in 3D space. So that's the specific house on the street. And finally, the spin quantum number, s, tells us if the electron spins clockwise or anti-clockwise, which tells us which of the 2 roommates in the house we're actually looking at.
And if you're wondering what the absolute maximum number of electrons is that can live in a given city or principal energy shell, you just plug that principal quantum number n into this incredibly simple formula, 2n squared. So shell number 1 holds 2 electrons, shell 2 holds 8, shell 3 holds 18, and so on. This simple little piece of math literally dictates the entire structure of the periodic table.
All right, Section 5, shaping the atomic world, visualizing the unseen.
So we have the address system down. Let's look at the actual physical architecture of these quantum neighborhoods, which is dictated by that azimuthal quantum number. As we go from S to P to D and F orbitals, the geometric shapes transition from simple to, well, incredibly complex. S orbitals are just perfectly symmetrical spheres, but step up to P orbitals and they look like dumbbells or lobes stretched along the X, Y, and Z axes. D orbitals look like four-leaf clovers, and F orbitals, they are so complex they look like bizarre balloon animal clusters. But what is truly awe-inspiring here is the concept of a node. A node is a region or a plane within these shapes where the probability of finding an electron drops to absolutely zero. The electron exists on one side of the node and the other, but mathematically it is never in between. Wild, right?
Section 6. Rules of Atomic Construction, the Rule Book.
To finish building our cosmic city, we really need to understand the strict regulations the universe uses to pack electrons into these wildly shaped orbitals. These three fundamental laws govern exactly how an atom is constructed from the ground up. Step 1 is the Aufbau principle, which is German for building up. It simply states that electrons are kind of lazy. They will always fill the lowest available energy orbital first before moving to higher ones. Step 2 is the Pauli exclusion principle. This is the rule that says no two electrons in an atom can have the exact same 4 quantum numbers. Basically, you can't have two roommates in the exact same house spinning in the exact same direction. One's got to be spin up, the other spin down. And step 3 is Hund's rule. If electrons are filling orbitals of the exact same energy, like those 3p dumbbell shapes, they will single file into empty orbitals first before they agree to pair up. It's literally exactly like strangers getting on a bus. People will sit in empty rows before they ever choose to sit next to someone else, all to minimize that repulsive energy.
But wait, Section 7, the rule breakers. When stability trumps the rules.
Because, nature always prioritizes balance. Take chromium and copper, for example. Based on the rules we just went over, you'd expect chromium to end its configuration with 4 electrons in the d orbital and 2 in the s. But actually, chromium steals 1 electron from its outer s orbital and pulls it into the d orbital to create a perfectly half-filled shell of 5 electrons. Copper does the exact same thing to achieve a completely full shell of 10. Why break the rules? Well, perfectly half-filled and fully filled orbitals possess symmetrical distribution, which reduces electron shielding. Plus, having parallel spinning electrons allows them to swap places, releasing something called exchange energy. This exchange energy actually drops the total energy of the atom, making it way more stable. So sometimes achieving perfect symmetry and stability simply overrules the standard step-by-step building code.
So we've journeyed from that flawed solar system model of the atom to a universe defined by probability clouds, complex geometric spaces, and strict quantum numbers. I want to leave you with this provocative thought to ponder after our explainer today. If the very atoms that physically construct our bodies, our planet, and our universe are governed fundamentally by profound unpredictability and probability, how certain can we truly be of anything at all? Thanks for exploring the atomic world with me.